And but I want to tell you that when I was at your position as a PhD student, I was doing experiments. My project is complete experiments, doing TM work. However, I like to use my brain when my hands were not busy, because you have to wait for equipment, right? You have to do all the things. So I started to do more and more theory. When I joined Penn State in '99, I was doing both experiments and computational work, and then a couple years later, I decided I'd do fully computational. So I've been fully computational work for 20 some years. Okay. So ask me what to talk. I'm going to talk about the unknowns unknowns be predicted. Okay, that's a big title, right? So we have to first define what do you mean by unknowns. Unknowns means that the property of a system before you measure it. That means you don't know the property. Okay, and the question is that what is the properties of a system? It's basically you can think about it as a response, right? You do this disturbance of a system, then since response to it, you measure it. That's the basic properties. You do different type of perturbation. You can put heat, work, and mass. There's three types of perturbation you can do. Okay. And then you measure the response. Of course, everybody have learned the Lascelles principle, right? Maybe learned once or twice or 3 times. I learned 3 times. And so when I was learning the last time in Stockholm, when Matsila gave the talk in the class, and he said the Lascelles principle has one exception. I don't know whether you learned that or not. Do you know what that one exception is?
That's the second time when you learn it that you get to know.
Okay. So what happens is that so actually because of the discussion with Matsilat, and we wrote a paper. And so we wrote a paper first, and Mats wrote this paper. But Matsilat is he can make the theory much more clear than we do, right? So I'm going to just go to the next slide. Okay, what happens is that it goes here. So what it means is that the Lascelles principle is that if you disturb a system, it's going to do something to undo that change a little bit, not fully, undo a little bit, right? So that means that if you add heat, the temperature goes up, then system can do some reaction, reduce temperature a little bit. That's basically what it means. However, there's one violation, well-known violation in the literature is that there's a reaction called the ammonia reaction, nitrogen and hydrogen from ammonia, right? So now if you think about this one, you add some nitrogen into it. Based on Lascelles principle, the system will do something, reduce a little bit nitrogen, right? Okay, so that happens most of the time. So for example, you look at the phase diagram, look at the property diagram. If you, suppose you're here first, if you add nitrogen, system will do something and bring it back a little bit. If you remove some nitrogen, system will do something, recover and produce some nitrogen. Right? That's perfectly okay. However, people by experiments, you find that if you add some more nitrogen, this is going to produce more nitrogen. So that's a violation of Lascelles principle in the literature. And so if you look at any textbook, you'll find it's a violation of this one. However, when I took a master's class, I said, that cannot be right, right? Lascelles must be right. So what's missing here? Missing here is that the disturbance in region 1 and 2, actually this one is okay, but it's region 3 is not. Okay, so the issue is that if you go to 3, you can see that, right? If you start in the red dot, if you do the perturbation, you're going to do large perturbation. You need large perturbation. Okay, so it's because your perturbation is too large. The system finds another equilibrium state. It doesn't go back to the original equilibrium state. It goes another state. Of course, that state can be completely different from what it had before. So we solve that problem. But unfortunately, if you go to today, if you go to chemical engineering, chemistry, people still talk about a violation of the Lascelles principle. I think you should go to read my paper. Okay? Unfortunately, they don't. So they're still teaching that the concept, the Lascelles principle is violated, but it's not. Because the Lascelles principle talk about the infinitesimal small change. So if you, after you change, you still return to semi-equilibrium system, it's okay. But if you change to non-equilibrium system, then the system, of course, doesn't obey the Lascelles principle anymore. Okay, So what does that mean? The lesson for this one is that we need to really be able to calculate all the equilibrium states. What does the equilibrium state mean? If you think about the energy landscape, that means you have many basins. If you have one basin, you fluctuate it, system always tries to go back, recover a little bit. That's the last percent. However, if you change so much, you get another basin. This basin doesn't know anything about that basin, right? So it doesn't care about the original basin you have. So it does whatever the new basin does. Okay, of course, the Laplace principle will break. So the idea is that you really need to get this non-equilibrium thermodynamics called the energy landscape. That's what Hillard really contributed to non-equilibrium thermodynamics. Typically, when you learn thermodynamics, you only have the first three terms, the TdS and the dW and this one. You don't have last term. This term is entropy production due to the internal process. Okay, if there is the equation, and the very important thing is called conjugated variables. The first term here is called conjugated external variable with control from outside. And this is one of the conjugated variables what's happening inside of the system. So Laplace principle trying to connect these two together. Okay, that means you have to do the differential change, small change. All right, so in order to do this kind of calculation, you have to get entropy, right? Yeah, entropy governs all the changes we have here. Okay, so how do you do entropy? Okay, then we have to, what is entropy? Okay, that's actually a very, very difficult question to answer. What is entropy? And people say entropy is randomness. Entropy is unknown. Entropy is uncertainty. Okay, you have a lot of things about entropy. So I wanted to check with Boltzmann 10 years ago, and he said, "Oh, entropy is S to the KB log W, right?" So you all learn that too. K is the Boltzmann constant. W is the number of configurations you have in the system. Okay, so that's a good answer. And why is it important? Well, as mentioned before, it's because the second law of thermodynamics, you have to be able to calculate it. Then you can calculate whether the process is possible or not. Okay, you have to be able to quantify it. So as we question how entropy is measured, I talked with the other professor. You know, you do heat capacity. Okay, that's right? Heat capacity. So that's what I did. You measure the capacity over T, the integration, you get entropy. That's exactly right, exactly true. Okay, you do experiments. And this, of course, has the important information behind it is that entropy at 0 Kelvin equal to 0. That's we can do the integration, okay? How do we know that entropy equal to 0 at 0 Kelvin? You can never go to 0 Kelvin.
The third law.
Third law. So how do you know the third law is correct? Because you cannot go to 0 Kelvin. So anybody, student know the answer? Of course, you look at the equation, right? That means if Cp over T goes to 0, then you say 0, right? That's exactly. So if people do measurements, but to very, very low temperature, they plot Cp over T as function of temperature, they find it approaches 0. Then they say, oh, let's just get a third law. Okay. So third law is not proven. It's a conjecture. It's the extrapolation of the heat Cp over T go to 0 Kelvin. Okay. But you never go to 0 Kelvin, right? It's funny, right? We believe something we can never measure. Of course, another very important thing I'm going to talk about is that we believe density functional theory because you cannot measure it. No, even though you cannot measure it, we believe it. Okay. All right. But how can we calculate entropy? So of course, I mentioned already, we have the Gibbs, right? I have the Boltzmann, Kb log W, right? But of course, you think about Kb over log W, that means it's a statistical mechanics. Statistical mechanics must have a probability. That equation has no probability, right? So that equation must be missing something. That means both my equation is missing some important message about the probability. Okay, of course, you know, that must be thought by the genius we had before, right? The person solved that problem is Gibbs. Okay, so Gibbs went to let's talk about experiment, right? For experiment, you do the experiment, you measure it, you get a model, you try to find fundamentals, then you do another model simulation and Monte Carlo, DFT, Monte Dynamics. The question is that can we directly go from here to there without those models? Is that possible? Okay, all right. So I want to talk about this very interesting story, which I learned because I teach thermodynamics for many years. It's the history of 150 years about thermodynamics. Okay, you know that so first law and second law. Second law was first law was a long time ago. Second law was developed during the Industrial Revolution, the engine, right? Engine, okay, engine. But the first law, second law has been separated for many years, okay? Because one is energy conservation, so it's equal. Another side is entropy production is positive, is non-equal. So equal, non-equal cannot be together, right? Because they've been separated for a long time. But of course, there's a great American scientist, is Gibbs. He went to Europe in 1866. And he looked around, he went to Paris, he went to Germany, and he listened to home health. He listened to those great scientists, thermodynamists. He came back and said, oh, he can do better. So he made the first law, combined first, second law. However, he made a trick. He said, okay, he tricked, so if you want to combine second law, you have to make it equal, right? When second law, entropy reduction is equal to 0, that's equilibrium. So that's a genius approach. So he developed this one, okay? And then he saw solve that problem, the entropy. Of course, that it has KB log W. That's Boltzmann entropy there. But he actually solved it more differently. He said you can have a probability. So he figured out the probability. So the equation now becomes different. I'm going to show that equation. He has the equation calculate entropy would be different from what Boltzmann had. He actually learned from Boltzmann, Clausius, and Maxwell, developed the statistical mechanics. You see time, right? Time is 1870s to 1900. He spent 30 years to figure that out. The genius spent 30 years to figure out it. That's going to be very hard, okay? So he actually solved the problem. He solved that problem. And then another big advance in science is quantum mechanics, which is 1920s, because 100 years now. And then we have the statistical quantum mechanics, quantum statistical mechanics too. Okay, that's another improvement of the Gibbs statistical mechanics by 1930s. But it take another 40 years until we get a quantum DFT to calculate, to solve Schrodinger equation. Okay, solve Schrodinger equation. And then you have non-equilibrium thermodynamics with Ansarg and Puligogin, and you have Kaplan modeling, that's what I studied. And the model non-equilibrium thermodynamics, and Hillard has these fundamentals of thermodynamics. That's 150 years. So think we have everything now, right? We have we have quantum, we have statistics, we have non-equilibrium, everything, right? So why we are still not predicting unknowns? Okay, that's because these three domains are separate. There are people doing quantum, there are people doing statistics, there are people doing non-equilibrium. Okay, they don't put them together. DP mentioned that then should be put them together. So then should be really put all three together to describe the thermodynamics of system. I know if you want to read, you can take a picture. Oh, you have you have the recording, so you can get this as a 9 papers I put together about the progress. 8 papers we put together about how we integrate them together over the years. Okay, so let's go back to quantum mechanics. That's the first one. Quantum mechanics is truly revolutionary in terms of that you have this the position and the momentum cannot be measured at the same time. So that means the quantum system has both the wave function, wave characteristics, and the particle characteristics. The two of them come together, so you cannot measure them at the same time both accurately. I think that's because we cannot measure faster than the change. Okay, so what it means, I have shown an equation talk about electrons and the nuclei, but the quantum mechanics is so, at least today, based on our understanding, is so fundamental because everything we have consists of electrons and nuclei. Doesn't matter what you have, it's always electrons and nuclei. If we have a function can describe this electron interaction and this nuclear interaction, then we should be able to predict anything, so to speak, right? Okay. But how to do that one? You have to do some approximation to solve it, and that was the DFT comes in 1964. And the idea is that for each system, that's again another big assumption, big conjecture. At 0 Kelvin, we cannot go to 0 Kelvin. There is one configuration of the system has lowest energy. That's called a ground state configuration. That configuration is represented by one unique electron density. That's really the theory. That's 1964. But how to solve it? You have a lot of approximations to solve that one. But over the years, the theory is becoming better and better. Today, it's pretty more and more accurate. However, you can never measure by experiment, right? So you cannot validate that prediction by experiments, okay? But you can calculate configuration. It's free energy. You can talk about it. You can start to vibrate the atoms. You can start looking at the electrons, so how it changes because it vibrates the atoms. Okay, so you can calculate the free energy of that configuration. However, we just about statistics, right? Statistics says that it's the other way around. It's the other way around. Statistics says that system has many configurations. So DFT do one configuration. You have hundreds of configurations, thousands, millions of configurations. The two, of course, cannot be together, right? They cannot be the same. Okay, cannot be the same. Okay, that's the exact challenge. So we started doing DFT calculation 20-some years ago. We always find that when we want to put this prediction with experiments, we have to refit the parameters. We have to refit it, use experiment data to make the correction. Okay. So that means we're missing something, right? Something missing in our calculation. So what are we missing? Okay. So now let's go back to what Gibbs did in 1901. Okay. Is that statistics? So we're missing statistics. I want to show this photo. This photo is by John Purdue paper in 2021, pretty new paper. And he pointed out, he developed a new potential called meta GGA for DFT calculations. The central point of meta GGA is that at the ground state, you have many minima. How do you use the function to represent all the minima? Previously, we used just one function, right? You know, as the PBE does basically. But he found that no, it's not. Actually, you have many minima along this trajectory and along the path. How do you use your functional to capture it? So that's what a scan potential came out in 2015, and they have a lot of revisions and improvements. 2021, I think it's probably final now called R2 scan. So the central idea is that the system complex. Anything you have is only part of it. You don't put all together, you can represent it. Okay, so what it means is that you have a system. You perturbate it, you have surroundings, you perturbate it in terms of three types of perturbation I mentioned. You have the heat, work, and the mass. And then you talk about the energy of the component, you put it together, you got a first law. But the most important is entropy, right? So what entropy we have? Heat, we have entropy, there's a Clausius entropy. And then component has entropy. You see, another question I have always the challenge is that the work never goes to the entropy equation. We always tell students that work doesn't change entropy. But the work does change entropy, right? Think about it, right? So what happens is that work affects internal processes. So you do have three entropy terms: heat, mass, and internal configuration, internal change. That's the second law. That's what exactly Maschilde did. Okay, that means, of course, that problem is solved by Gibbs in 1901. He said, if a system can access all kinds of configurations, right? Okay, then you can calculate them by the partition function. Okay, and then you can calculate entropy, and you can calculate the probability. Okay, so another idea is that each configuration has a probability to exist in the system. But when you do measurement, you sample all of them. So your experiments is a sampling of all of them statistically, not just one, not just two, all possible ones. If all of them have the same probability, that's P equal 1 over W. That's Boltzmann entropy. Then you got this S equal to KP log W. What does that mean? That means Boltzmann entropy is a special ideal case when all configurations have the same probability. Of course, that doesn't exist in the nature, right? Any configuration always have different probability. Okay, so that's why many people use that equation KP log W. Of course, the entropy is incorrect, inaccurate, right, compared to what the reality you can measure. All right. So what is entropy? Again, entropy is not my invention. We talk about our method, And in 2021, I gave a talk, and we said it's not our approach, a little bit different from statistical mechanics, from DFT, but put them together. And there was one postdoc there online from Buffalo. He said, you should call it Zentropy. We love it. So since 2001, we got 2021, we call it Zentropy. Okay. So entropy is basically Z plus entropy. Z is the partition function, right? Entropy. So partition function for entropy. Of course, we have entropy already in the partition function. So what's the missing part? We'll talk about that. Z is the German word Zustandssumme, the summation, and it's partition function. Okay. So the only thing we're going to change is that zk. How do we represent zk? Remember, if you go to Gibbs equation, zk is the exponential minus ek divided by kBt. Ek is total energy. Therefore, does that. Same thing in the quantum statistics mechanics. So that's what we have. So a system has many configurations, right? Okay. Experience all the configurations is different probability, pk log pk. That's what we have. And all the configurations are called symmetry broken configurations, exactly like John Purdue said in this symmetry broken configurations. However, that's the equation we have for the Gibbs information or Shannon information entropy. However, each configuration may has its own entropy, right? If that configuration is a pure quantum configuration, no internal degree freedom, that has no entropy. But when we do DFT calculations for the ground state, it has entropy. Okay, because if you increase temperature, it vibrates, you get the phonon. And then when the phonon vibrates, electrons redistribute, you get another electron contribution too. So that means we can predict it by quantum mechanics today. DFT, any configuration today, basically. You can predict the phonon, get the entropy of each configuration. So, but that equation from Gibbs did not include that part. Right? It doesn't have that information. You don't have the pk. So then we say, okay, maybe we should have both parts. Okay? So that means the entropy of the system should have two parts. So one part is the statistical amount configurations. Another one is configuration, each configuration itself. Each configuration has a probability, so PKSK. So that's basically what we proposed. The reason we proposed this one because we find if we don't include that one, if we don't include the first part, we do DFT, we get the second part, it doesn't agree with experiment. Then statistically, of course, doesn't agree because it doesn't have quantum entropy. Okay. So then we find it agrees with the heat capacity measurements. So that's very good. And what I find is that we need to only change one thing. We need to only change from before we had EK, change to FK, including the SK inside. Then the equation is exactly the same. So it's still statistical mechanics. The only thing is that you consider the entropy of each configuration. That's called the sum of all the configurations together. That's why I thought the entropy is the perfect name for it. You sum up all the entropy in each configuration. So of course, then we try to solve a different problem. But it's very important we realize later is that statistical mechanics is not for equilibrium. That's very important because when you do statistical mechanics, each configuration must have the same condition, same MVT. If you do the canonical ensemble, that means basically statistical mechanics only gives a homogeneous system because everybody have the same MVT. Only difference are the configurations. Okay, they mix together, you get a homogeneous system. However, this homogeneous system could be stable, metastable, unstable. You can do the perturbation and find them stable or not. Okay, and actually you are calculating the homogeneous energy landscape. That means you include all the basins, all the saddle points, all the apexes. That means you can calculate the barrier between two states with different configurations. Okay. So as I mentioned that we actually have a paper, as a book come out, 2 volumes, which combine our papers together, that is entropy, 2 volumes there. But it's even more important to realize that we can calculate the entropy of unstable state because into derivative only. You don't need to calculate the phonons anymore. Phonons are already calculated for stable configurations. So the unstable state is purely because of the competition. When competition becomes so severe, the system crashes. Okay. All right. So the first case we did was cerium. Cerium is that you can see cerium has this FCC a structure. So it is the ground state. This is alpha. At 0 Kelvin is non-magnetic. Okay. At those FCC, high temperature is ferromagnetic, gamma FCC. And then, of course, you will find is a critical point, which is measured, but it's never predicted in the literature because a critical point is where system crashes. So you have the singularity. And then we found we should have an intermediate configuration called antiferromagnetic too. So calculate the energy of it. You can see that the ground state is red one, and this AFM is a high energy. AFM is between. Okay, we'll take 3 states. We'll calculate all the energy. Then we can put them together to calculate the energy as function volume. So we do find. We find at 0 Kelvin. You have this one side, because this 0 Kelvin just do tangent, right? Between these two. Okay, that one's above, so it doesn't matter. But when temperature goes up, that one starts to contribute to it. Okay, then you see this is some small change here. That was the configuration entropy, PK log PK. That means you can calculate the barrier between two states. One is alpha dominate, another is the AFM dominate. Okay, then we calculate the barrier, free energy barrier. The barrier changes with temperature increase because KBT. So it becomes more and more dominant. At one point, it becomes 0 barrier. That's the critical point. Okay, so you can calculate the PD diagram, get the critical point, which shows up here as a temperature pressure phase diagram. And now you can change the pressure to volume, which is a conjugated variable. That's very important when I learned from Bas Hillard. PV as a conjugated variable. You calculate the PV diagram, you can split the gap. You get a critical point and split the gap. It's between volume and magnetic properties. Even more important, you calculate the divergence of some expansion. Some expansion becomes infinite. Okay, that's the instability happens there. Then we look at the next problem is UMA. I hope you heard about UMA. Is that some expansion volume decreases, the temperature goes up. You get negative sum expansion. So this negative sum expansion as a linear sum expansion as function of temperature for this iron 3 platinum. The sum expansion always positive, increase, then start to become decrease and become 0 if you get negative sum expansion, and then become positive again. Volume decrease with temperature. Of course, there are many theories that try to explain me, kind of mechanism and so forth. Say it's the softening of the bonding and the phonon, everything, right? So then we thought maybe we can use our method to solve it. So we have the iron has spin. We take the very simple spin configuration, up and down, collinear spin. We have 250, 512 configurations. Symmetry-wise, we have 37 of them unique. We looked at all the structures. We calculate their total energy at 0 Kelvin. You see immediately very interesting thing. All the metastable configurations have smaller volume than the ground state. In the previous case, the metastable has a large volume. It's because the smaller volume, when the probability increases, the total volume decreases. Even every configuration volume increases with temperature, but put them together, the volume can decrease. So there's nothing to do about softening at all. Softening is just a phenomenological observation. All right. So when calculate the free energy, we show that the ground state is always stable, so energy-wise. But if we put them together, we can see the probability decreases. And then we can calculate all other kind of anomaly properties. Of course, we calculate PT diagram too. And this time we find that the sum expansion, the volume as a function of temperature in certain area, it actually decreases. That's because the smaller volume one, they replace the bigger volume one. The total volume decreases. Even though each of them, their volume increases with temperature, but put them together decrease. So it's a purely statistical mixture of those different configurations. Nothing to do with bonding. Bonding, of course, you can measure it. You see the bonding is weakening because you do the average. Okay? If you look at it individually, the bonding is not weakening at all. All right. So we did more calculation. This is our prediction. We kind of more calculation recently for the strongly correlated physics, like ethylnicolate. Again, we predicted beautifully with experiments. Again, no fitting, purely from the DFT and the statistics mechanics. We can predict short range ordering. The last one, I'm going to examine liquid and metal, liquid. And you do empty simulations, you do the calculate the properties, you do the average. you find that you can never predict the melting temperature accurately. Okay, and then I couldn't solve the problem. I then asked Professor Qi Junhong from ASU, can he help, because he does a lot of MD simulations. So the idea is that they then figure out how to calculate the actual entropy. Okay, so he found that in the solid is the coordination number 12 FCC, so it doesn't change. But in the liquid, the coordination number changes. So you get distribution. So as soon as I get distribution, you get entropy, right? The probability. So you calculate the probability for liquid aluminum here. The entropy configuration is 6.35 joule per mole. That's a pretty small number because the vibration entropy is like 60, so 10%. 10% of the entropy. However, remember the melting temperature is not absolute entropy. Melting temperature is calculated by entropy difference, right? So that means that as between the liquid and solid before is like 3 joule. Now you add 6 joule on top of it. That means the temperature will be different by a factor of 2 or 3. That's exactly the case. If you do the MD simulation, you find the melting temperature is like 3000 Kelvin. Okay, but you do measurement, it's 1000. That's because they miss entropy there. That entropy is only 10% of total entropy, but it's 50% or more of the entropy change. Okay, that will make a difference. So then he calculated many systems, and very, very nice agreement. The paper is being submitted for publication. And then we want to do more things, a superconductor. So we had the DOE project to predict superconductor. Okay, the idea is that at 0 Kelvin, if you take any calculations, can you tell that a material is a superconductor or not? At 0 Kelvin. Okay. Of course, you know you cannot do it, right? You cannot do that. It's because the reason because we know the BCS theory of superconductor is Cooper pairs, need 2 electrons, right? At least from the pair. DFT itself is a multi-electron, but however, the solution we have is a single electron. So 1 electron problem. We don't talk about electron-electron interaction directly in the DFT calculations. So that's why if I talk with people, they said, no, you cannot do it. DFT cannot do superconductor. DFT cannot do the Cooper pair. I said, that's absolutely right. However, the DFT does take the electron-electron interaction into consideration through the potential. The electrons are independent, but they interact with each other through the potential. What does it mean? That means the electron density must be correct. Okay, that's right. So we did that one. And remember that the superconductor is electron-phonon interaction, right? So what we did is that we take a symmetric, again inspired by John Perdue's work on this scan. So we take FCC aluminum. Okay, if you do FCC aluminum, it's highly symmetric. It's not going to form Cooper pair. However, if you destroy that symmetry by displace the atoms, that's the phonon, then the phonon displacement will affect the electron structure. The electrons should form Cooper pair. Of course, what is a Cooper pair? We cannot know what it is, right? But we figure out that we try to search. We search if we disturb the atoms, break the symmetry. We try to find out what we can see. That's what we see. So we saw that electron density. So what happens is that we find that if from this kind of one-dimensional channel, that means you have a kind of a superhighway of electrons that go straight all the way across the whole lattice. So when the electron moves, they don't have resistance. Of course, we have to test different hypotheses for different superconductors. We take like 18 pure elements. So we find that most of them agree. There are 3 of them do not: copper, silver, gold. Okay, our theory, our calculation shows that copper, silver, gold, one more I forgot now, should be superconductor, but no experimental measurements. People tried to measure it, they couldn't find it. And it turned out, if you look at literature again, if they're superconductor, their TC is like 0.2 MK, millikelvin. So you cannot measure. Some of them 10 to minus 6 millikelvin. Okay. So of course, then we go to another side. We say, let's do YBCO, right? YBCO is a high temperature superconductor, right? Okay, that's actually what we did. So take WebCO. It's so interesting. So this is the one you have. So you see that you have the one-dimensional connection here, electrons. That means it's one, but this one has very low critical current because this connection is very small. This aluminum is big, actually. Okay. Of course, then we have to explain why the YBCO goes high temperature, right? And the aluminum is low temperature. Okay, I leave you to read that paper if you are. It's on archive. You can go to read it. The idea is that the structure of system is very different. YBCO has a very different structure, overall structure compared to aluminum. Okay. All right. So actually now you can calculate many properties now. You can predict any properties even before you measure them now. You calculate the free energy, you calculate entropy, you calculate the free energy, you do derivatives. All your measurements are derivatives of free energy. You perturbate it, see the change in energy, and respond it. So it's all derivatives. You can, this is second derivative, give you all the properties we can measure. Okay, some expansion, elastic compliance, and periodic electricity. It's all second derivative to different quantities. Okay, and there's a new type of quantity which we have not largely overlooked. It's at least when I was a student, Mazhila said, well, you cannot do it. For example, chemical potential to temperature derivative. What is that? Chemical potential to temperature derivative. Okay, and I still clearly remember I said you cannot do that derivative. You cannot do derivative of chemical potential to temperature. I said, why not? It turned out we did. Okay, so actually you can calculate all the potential derivatives. So one of the very important parameter we measure of this one is some electricity, Seebeck coefficient. Seebeck coefficient is that you get some electron material, right? You get a temperature gradient, then generate electricity. Okay, what does it mean? That means temperature changes the chemical potential of electrons. That means you want to calculate Seebeck coefficient, you have to calculate the chemical potential electrons to temperature derivative. That's our hypothesis. Let's try to understand. We did it. So we did Seebeck coefficient. Now Seebeck coefficient, in our understanding, is just a derivative. It's not a kinetic coefficient at all. So you can construct this flux equation of current, and then you can tell a steady state. That's how to do experiments. Then you measure the voltage, you calculate Seebeck coefficient. However, if you compare the relation here, that Seebeck coefficient is chemical potential of electron to temperature gradient as the minus entropy, partial entropy of electrons. Okay. Of course, we have to prove that. So we did a calculator for tin selenide. And again, the symbols are experiments and the lines are prediction. This is the p-type. Then we calculate both p-type and n-type doping for lead titanate, lead ternide. And again, it's a remarkable agreement. Think about these measurements are very hard to do. And they also calculated for another one, is this n-type of Seebeck coefficient. All right, so I want to close my talk. Is that so I was asked about a paper about our quantitative approach, and the answer four questions: keeps the equilibrium thermodynamics, here the non-equilibrium thermodynamics, and the entropy theory and the theory of cross phenomena like the Seebeck coefficient. And I want to thank you, really appreciate what I learned from Max Hillard. So I wrote a paper for him. He passed away in 2022 at the age of 98. So last year it's his 100th birthday. So we had a special issue for him. And I want to summarize the work is that we believe, and we demonstrated, by putting the statistic and the quantity together, we can predict the things which we have not measured before. Okay, and it's purely based on the DFT. So of course, that question is, is DFT correct? Okay, that DFT could be improved. Actually, even more question is quantum mechanics is fully correct or not, right? But today's knowledge, quantum mechanics is the foundation. DFT is the only tool we have to predict things we do not know. Could be better ones in the future, but today we don't have it. Okay, so the next question, of course, is machine learning, right? You can do machine learning, right? Okay, so we actually do machine learning now. We're developing a new network called the entropy enhanced network. The idea is that machine learning today has a very complex network with a billion trillion parameters inside. Because it's so complex, right? But if we thought maybe we don't need that complex network. Okay, just like how DFT solved the quantum mechanics. Quantum mechanics could not be solved directly because of too many electrons interaction. Right? You cannot solve it. But if you put in the DFT theory, you solve it. The results are reasonably good, or the best we could have today. But now if you do machine learning, not learn individual layers, but we learn the configurations. Because we know any system is composed of configurations, right? From statistical DFT point of view. So we are proposing new learning, learn the configurations. And first learn the Frenzel configuration, then learn how many configurations you need to converge your machine learning network. So that's our approach now. It turned out we were so happy or unhappy is that people are already using it. So 2 papers here. So we're talking about how to do it. Then the one junior professor searched the internet. Oh, said you guys is already used by people. So the one group used this entropy to the classification. Okay, feature selection. That's very nice. So we are going to learn from them. Actually, we are working on it. Hopefully, we're going to have to present a new network, configuration-based new network. Okay, so I want to mention that I'm an old person now. I'm going to retire one day. So how could I keep what I know into the literature? Of course, there are books. I have books. But if you want to scan this place, or you go to that website, I'm going to record all some of the names I know. I have now 11 lectures there, 12, I think 12, 11. Okay, anyway, so I'm going to record one tomorrow. Okay, I'm going to continuously record them until I could not speak anymore. So I want to, actually, I'm going to have it that if anybody has questions, you have a topic. This topic-based recording. It's not just the good lectures, okay? So I have first law, second law, third law as 3 lectures. Then I have the combined law is another lecture. I have the Gibbs phase is 1 lecture, and so forth. The next one lecture is phase diagram. That's the next lecture. So lecture is like 5 to 20 minutes. So you can listen to it during coffee break. Okay. Thank you very much. Thank you.
Yeah. And give the hierarchy of system entropy to configuration. Now, I think you might have mentioned there's only one configuration where it's equal to 0, right? Do you see
That's one configuration has lowest energy. That's right. That's exactly the point. That means there are many configurations which, due to the internal degree of freedom, and has a high energy.
my question is, the temperatures above 0 Kelvin, do you see some sort of relationship between the temperature and the number of configurations?
That's right. So what happens is that at 0 Kelvin, only one configuration is activated. That's ground state. But when you increase temperature, all configurations become possible. But the probability of those configurations depends on the energy difference, right? So if the energy difference is very small, medium Kelvin is high temperature. So it's relative to the configuration energy. So of course, the question is that what kind of configuration to consider, right? So that depends on your problem you want to study. So for example, we study magnetic, we change the spin configuration. We study polarization. For electric, we do the different polarization configuration. So superconductor, we don't know what the configuration yet. We're still trying to figure out. Yeah. In principle, you should only one set. Okay, for example, for the magnetic material, right? If I get this configuration, I can predict all the properties for the magnetic material. But of course, the question is that you may not capture all these configurations. You do not know, right? So you can do the conversion test. You can add more configurations, see whether the property converges or not.
So, as you raise the temperature, right?
Yeah.
Every temperature, let's say 1 Kelvin scale, the probability of a different configuration
Changes.
would be higher, right?
Yeah.
One configuration may dominate at a given temperature and you raise. So how do you know which configuration dominates at what temperature?
You calculate it.
And well, it sounds like a cluster expansion of configuration.
No, it's,
So how do you determine that deterministically?
so that's, you don't do that either. So supposedly the configuration should be ergodic.
Sorry, what?
Ergodic. You have all of them.
Okay.
Okay. So what you do is that for this case, we do to the 2 to the 9th power. Right? We do 2 to the 9th power is because our supercell has 9. Yeah.
Yeah.
It's 12 atoms.
Yeah.
9 atoms. Of course, if you increase large supercell, that's fine too. Right? You get more configuration.
Yeah.
However, we
these are exhausted, right? These are exhausted 512 for this.
all of them. You don't have anything more.
Yeah.
That's it. However, you have another one. People say you have non-collinear, right? But we talk about collinear only up and down. But people say no, you have up this way, right? And that way. Okay. So I think that is just observation. Is correct. However, what happens is that we have spin up and down. But if you spin, when the spin is rotating, right? You have to rotate it down, right? When the rotating process could rotate this way, could rotate that way, could rotate this way. That's what you observe. That means you observe rotate all different directions. This is it's a non-collinear. But it's collinear itself, we described already.
So this is, I don't want to call it simpler, but system is simpler, it's pure serial.
Yeah.
When you have binaries, complexity goes up.
That's right. That's right. That's right. Wow, so you cannot. You cannot do all the calculation with DFT. That you take all the computer power in the world is not enough. That's why do machine learning.
I was hoping you would give that answer.
No, that's right. So you cannot do it. That's why you have to do machine learning. That's why you have to train your neural network to predict the free energy. Instead of use days, you take minutes.
I still have my job.
Yeah, that's right. Absolutely. That's the only way to solve the problem.
Our question.
Yeah. So what we do actually is 3 things, machine learning. We first learn the energy at 0 Kelvin. That's the first one. Then we are learning these 2. Okay, that's 3 models now, right? You have one for the E, one for the SEL, for the S phono. 3. That's 3 neural network we developed. And then put together, you get F of that configuration. That's a machine learning model. Then just put them together, use the entropy to calculate the properties. Of course, you can do another machine learning model is that you just learn everything, right? That's what this big language model does. Okay, you learn everything, but that's a black box learning. But we think that if we know the science, we do science-based learning, basically. Yeah, so at the moment, we can calculate from DFT. Okay, so you take the calculation from DFT as training data to learn this one. Then you build up this model and that model and the E model. Then you calculate the FK, basically. You predict the FK. So of course, you can do one model, just learn FK, right? But that's very complex. That's why you need so much data. You need the temperature, you need the composition, you need the different arrangements. That's a lot of things to learn. So we think maybe break it down a little bit lower level, it would be easier. Yeah, that's right. So that's what I'm doing now. But I really like DP does now is that so DFT calculation is basically calculate the electron density, right? So we call it electron structure. So DP want to learn the electron structure. That's beautiful. That'd be very beautiful because that means give any structure, you can directly use machine learning to calculate predict the electron structure. Then for electron structure, you do integration, you get all these properties. That's even more fundamental level below what we are learning. Yeah. So if he's successful, we can scrap all machine learning models, just take his.
Put everybody out of job.
Get water temperature.
Yeah, so it's actually, I don't have project on that, okay? And I have a theory for the why water has negative thermal expansion below 4 degrees C. It's because the different configurations. Some of them are the ice configuration. Ice configuration has a larger volume, okay? So that means now when the temperature decreases, this larger volume becomes dominant, increase probability, so the whole volume increase rather decrease. The question is that we need to get those calculations, right? So I needed somebody work on water. Yeah. So the point is that this supposed to avoid that problem. So the problem is avoid that because you calculate the configuration temperature with each configuration separately. So the overall behavior is a competition. So you don't predict the overall behavior at all, because that's very hard. It's almost impossible in my opinion. But you can predict it individually because individuals are well defined. It's well defined structure. If you do that one, then you can do it. So now remember, you see, I mentioned I just solved liquid, right? Melting. The next one will be the water. The way to solve that problem is that if I have an expert on water, that's the best. So I couldn't solve that myself. I have an expert on liquid. So he solved it. So anybody works on water, I would love to work together.
Geology department. You guys are in.
Yeah,
it's
right. I think, you have to be both people interested.
Can I ask another question? So, okay, so BCS connects TC to divide.
Yeah.
You're saying that there's a way to predict TC without any of those assumptions.
That's right, with zero assumption. Maybe you see, I just wrote my renewal proposal for the next 3 years. So I should hear it by maybe a couple of months. If I convince them, then they give me money, right?
How close are we in room temperature superconductors?
So I'll tell you, that's hard, right? Okay, so I told the program manager in my proposal. So the idea is that we have a database with 4.5 million structures, configurations with different chemistry. So I'm going to use my theory I just presented, screen off them, see which one has potential, which one are the superconductors, which are not measured yet. Then we calculate the condensation energy. That we can do from DFT. So then we rank the condensation energy. We find the biggest one to start. Okay, that one should have highest TC. Then we look at the internal structure and see whether it's possible to sustain, to preserve those tunnel I mentioned to high temperature. The two criteria. First, you have the large condensation energy, and then the tunnel is protected by some kind of structure inside in the system. Layer structure, actually, layer structure. If that's the case, then we have few people wrote a letter for us. They can do experiments. Okay, so we give them 10 materials, 3 groups, and to make them see whether we get 200 Kelvin DC.
Okay, if not, let's thank our speaker.
Thank you, thank you, thank you very much. Thank you, thank you.